we are going to look at the preparation of an alcohol from an epoxide. So as a reminder of how to make an epoxide, you would be using a peroxy acid on an alkene. So for instance, if I had a real simple alkene, we'll say this is the alkene I'd have, you would use a peroxy acid like MCPBA, or maybe peroxyacetic acid itself. One of these. The main thing is you're looking for a peroxy acid, and it will produce for you an epoxide. Okay? But if you have an epoxide, you can use it to make an alcohol as well as a carbon-carbon bond during the course of a reaction. So we're going to redraw the epoxide I just made. And what you would see is a two-step process. So the first step of this would be to use either an organolithium or a Grignard reagent. I'm going to keep this very simple, and I'm going to use a Grignard reagent. And when you make Grignard reagents or organolithiums, again, remember that the solvent choice has to be one such that it does not have an acidic proton. So diethyl ether is a really good choice for something like this. And then you would follow this up with acid, but it would have to be a two-step process, because if you add acid initially, it will protonate the Grignard reagent and you will have no reaction. So this literally does have to be two separate steps. So you have an epoxide. Several things to remember about epoxides. I'm going to draw out the hydrogen here as well. Epoxides have a three-membered ring, so there is a lot of steric strain on that little three-membered ring. The bond angles there are about 60 degrees, and normally with sp3 hybridized carbons, they would like to be around 109.5. So there is a lot of angle strain on this ring, and it would like to break a bond to relieve that angle strain. So these are the chemical species we have in solution. Again, do you like to think of things in terms of anions? Because they really are anions. And this way you can see the carbanion. It's the conjugate base of a very weak acid, so they don't get any stronger. It wants a proton if it possibly can. This is why the solvent choice is an ether, so that you don't pick up that proton. Now, as it comes in solution with this particular epoxide, this is very much like a tent reaction. It's going to be the mole that burrows underneath the tent and attacks. And if you remember from what was told to you when you looked at halohydrin reaction, or the vicinal addition of halogens to an alkene, this is basically the same story. So in this case, your mole or your nucleophile is the carbanion, in this case methide, and it will be reacting with this epoxide. Now the epoxide is trying to stabilize itself. The oxygen is more electronegative than the carbons, so the carbon-oxygen bonds are polarized toward the oxygens, meaning that those two carbons in that little ring are somewhat positive. And the tertiary carbon is a better electron donor than the secondary carbon, so it bears a little bit more positive character. This methide literally can add to either carbon, and it will, but it is more likely to add to the tertiary carbon. This is much more likely because it's a little bit more positive. Now, as it's adding, this is basically an SN2 substitution. It's doing this backside attack. You have to break a bond, and the weakest of these sigma bonds is the carbon-oxygen bond, and oxygen is more electronegative, so it'll take those electrons with it. The other option is for the methide to add to the secondary carbon and break the carbon-oxygen bond here. So there are two different products that will form. The major product or the major pathway will be through the blue pathway. So you can draw out those carbons. If I added the methide to the tertiary carbon, this is what we're going to end up with. this is the major product. If you'd gone through the minor product, if you wanted to make the minor product, I have to remember what color I used, you would have added it to the secondary carbon, that methide. But it literally could have added to either one of the two carbons in that 3-membered ring. Now this is where it will stay. These would be paired up with the magnesium and the bromide. So charges are going to balance here. And this is where you will stay after step 1. This is what you have. And this is a weaker base because this is an alkoxide. That is a weaker base than the corresponding conjugate base of an alkane like that methide. So this was very favorable acid-base chemistry. But it is still a strong base. It's just not as strong as it was. So now we add in the proton. So we're going to bring in our proton source. I'm showing that as a hydronium, but you could use any acid you really wanted to here. If it's from the strong base, or sorry, from the major product, you're going to use the oxygen to pick off the proton and give electrons back. If it comes from the weak base, you're going to pick up the minor products, you're going to pick up the proton and give electrons back. So you're going to get 2 products at the end of the day. Now, if I had done this in such a way that you ended up with chiral carbons, I made sure I didn't in this particular case, except for right here. If you had chiral carbons, be aware that this always does an anti-addition to the epoxide. So the OH group and the carbon group that are being added across the epoxide are always end up on opposite sides. It's always an anti-addition.